All right, today we're diving into something that is seriously going to bend your brain. We're talking about a wild new experiment that's testing quantum entanglement. But, and this is the key, it's not just about that spooky connection across space. It's about seeing if that link can be stretched across time itself. You know, we've all heard the line, when you measure one entangled particle, its twin instantly knows what's up, no matter how far away it is. But here's the thing, that description's always had this kind of hidden assumption baked in, that both measurements happen at basically the same moment. This new experiment asks a pretty radical question. What if they don't? What happens if you add a delay?
So just as a quick refresher, right? Quantum entanglement is this incredible link between a pair of particles, let's say photons, where they're essentially one system. If you measure one and find it spin up, you know for a fact that its twin is instantly spin down, even if it's light years away. This is the very thing that freaked out even Einstein. He's the one who called it spooky action at a distance.
For the longest time, testing this link has been all about conquering distance. I mean, scientists have sent these entangled photons across entire cities, they've beamed them up to satellites, stretching the connection over hundreds of kilometers, but they've always measured them in the same tiny slice of time, just to prove that connection is faster than light. In this slide, it really shows you this simple but totally profound shift in thinking here. On the left, that's the standard test we've been talking about. 2 measurements, boom, boom, same time. But the new protocol on the right, it completely shatters that mold. They measure particle A, and then they just wait. They deliberately put particle B on hold before they check its state. And that, right there, leads us to the huge question that's driving this whole thing. We know the quantum link can survive distance, but can it survive time? I mean, does this spooky connection have, like, a shelf life? The whole point of this experiment is to create a time delay that they can actually measure and control. So this isn't some accident or a slight mismatch. No, this is about intentionally measuring one photon while its cosmic twin is basically put in timeout before its own state is revealed. So how on earth do you put a photon, a particle of pure light, on hold? I mean, it seems impossible, right? Well, scientists have come up with what you can basically think of as a time delay machine, and they've got 3 really distinct, really fascinating ways to pull it off. So here are the 3 main approaches. First, you've got something called a quantum memory. This is amazing. They use supercooled atoms to basically trap a photon, like hitting a cosmic pause button. The second method is a bit more direct, fiber optics. Just send one photon on a really, really long detour through kilometers of cable, making it show up late to the party. And the third method, it is straight out of science fiction. They use relativistic motion, like spinning one photon at crazy high speeds to actually slow down its personal experience of time compared to its twin. And we're not just talking about these tiny little delays that you can't even perceive. This whole protocol is designed to create real, macroscopic time separations. We're talking everything from nanoseconds all the way up to actual seconds and maybe even longer depending on the tech. On a quantum scale, that is an absolute eternity. Okay, so let's say you've done it. You've successfully delayed one of the photons. The big question is still hanging in the air. How do you prove it's still entangled? How can you be sure the spookiness actually survived the wait? Well, for that, physicists have a really powerful tool up their sleeve. It's called the CSH inequality. Now, don't think of it as some scary, complex equation. It's much simpler than that. Think of it as a rulebook for reality. Any system that behaves the way we think it should, according to our everyday classical world, has to follow the rules in this book. It sets a hard limit on just how correlated 2 separate things can be. And this is the line in the sand. After you run thousands of measurements, if you do the math and your correlation score comes out to 2 or anything less than 2, then your system is playing by the classical rules. No spooky connection. The particles are just acting like 2 separate independent objects. But, and this is the magic moment, if that score is greater than 2, you've done it. You have broken the classical rules. You have definitive mathematical proof of quantum entanglement. A score higher than 2 means those particles are still one single, spooky, interconnected system, even after one of them was forced to wait through time. And this is where it gets so exciting. Because this is a real experiment, right? Which means it offers up several testable predictions. There are a few different ways reality could actually behave here. And every single outcome would tell us something profound about how the universe really works. So there are three main possibilities. First, you could see what they call perfect persistence. The entanglement just survives perfectly, no problem, exactly what standard quantum theory says should happen. Second, we might get a relativistic warping. The connection is still there, but it's been changed by a phase shift. Think of it like a perfectly synchronized dance where one dancer's timing gets just a little bit off because of their weird journey through time. Or there's the third possibility, connection breakdown. The link just breaks. The longer the delay, the more the outside world interferes, and that delicate quantum whisper just fades away.
So why go through all this trouble? Because this experiment, it's not just about entanglement. It's about getting at the biggest puzzle in all of modern physics. That deep, unresolved fight between our two best theories of the universe. You've got quantum mechanics for the super small and Einstein's relativity for the super big. The problem is, they just don't play nice together. And finding where they break is the absolute holy grail. As the researchers themselves put it, this protocol isn't just a single experiment. It creates a whole new experimental platform for exploring the interplay between quantum information and space-time structure. That is a huge, huge statement. What this really is at the end of the day is a new kind of laboratory. It lets us run tests right at that messy, mysterious crossroads where the bizarre rules of quantum mechanics smash up against Einstein's ideas about gravity and space-time. It's a brand new tool for figuring out how these two great pillars of physics actually speak to each other. And that leaves us with this final, amazing question to chew on. For about 100 years, entanglement has messed with our ideas of space. Now it's coming for our ideas about time. If this fundamental quantum link can actually hold on, not just across vast distances, but through duration, well, what other incredible secrets about the nature of reality have been hiding in plain sight this whole time?